Hi class, this is our last lecture in chapter 12. So in this lecture, we're going to cover sections 12.5 and 12.7. And 12.5 is about collision theory and the theory behind chemical reaction rates. And then in 12.7, we're going to briefly cover catalysts. And so let's get started. I'm going to share my screen and we'll look at the Microsoft PowerPoint I had set up. Actually, I want to share my desktop. Okay. So here's the desktop and my PowerPoint. I'm going to make it full screen so you can see it. So chapter 12.5, section, first we're going to talk about collision theory. Hopefully you'll understand it at the end of this video, and going to learn about the temperature dependence of reaction rates. Also be able to generate and use graphical representation of data to determine the reaction activation energy. That's an example on the worksheet. And then know how catalysts affect reaction rates. So the topic on catalysts is in section 12.7. So collision theory, there's three basic postulates. The first one has to do with that the reaction rate is proportional to the number of collisions in a given amount of time. So that's collisions between molecules or atoms. It's the collisions between the reactants in a chemical reaction. If it's a single reactant, it's a collision between the reactant molecules. So we already learned that concentration, the number of collisions is going to increase as the concentration of the reactants increase. So this is where the concentration component in the speed of a chemical reaction occurs. Second postulate has to do with the correct orientation. So if the reactants have to collide, or the collision occurs, they have to collide in the correct orientation. And there are a couple of graphic representations to try to get you to visualize this. The third postulate. Oops, what happened here? The third one. That there's enough energy to penetrate the valence shell. So we know that a chemical reaction occurs, it's occurring with the valence electrons. And so when the reactant molecules collide, they have to collide with enough energy so that the valence bond electrons in the reactant molecules can break and form new bonds with the product molecules. So that requires the valence shells. The valence shells are electrons are negatively charged, so they're electrostatically they're going to repel each other. It takes a lot of energy to get them close enough together for bonds to break and new bonds to form. So those are the three postulates of collision theory. So we're going to talk about that. We're going to talk quite a bit about energy in this unit. So regarding postulate 2, the orientation, here's an example of a chemical reaction between nitrogen monoxide and chlorine. And the product, in the case of the product, there's a new bond formed between the nitrogen and the chlorine. As you can see in this example, and I'm moving my mouse here. I hope you can see the mouse. I noticed it wasn't showing up before. But the cursor, I'm pointing at the chlorine molecule if you can't see it anyway. So you can see the chlorine molecule is oriented directly at the nitrogen of the nitrogen monoxide. So when they collide with enough energy, a new bond will form between the chlorine and the nitrogen, and the bond will break between the chlorine atoms to form the products. So this is a correct orientation that leads to product. In the second example, in part B, the oxygen of the nitrogen monoxide is oriented towards the chlorine molecule. So when those collide, no reaction takes place. The molecules just bounce off each other and you're left with nitrogen monoxide and chlorine. So that's really an important point, is this orientation. The orientation is random. You know, so the molecules are spinning and vibrating and going very fast. And so the orientation, the correct orientation doesn't occur all that often. Postulate 3 has to do with the enough energy for the reaction to occur. So this is a schematic that shows, again, with nitrogen monoxide and chlorine, that when they collide, if they collide with enough energy, there's a complex form. It's called the activated complex. And the activated complex, we always put that in brackets because it's a very temporary chemical structure between the atoms involved in this chemical reaction, where the bond between the chlorine atoms is breaking and the bond between the nitrogen and the chlorine is forming. So if there's enough energy, this reaction goes forward. If there's not enough energy, it goes backwards. It goes back to the reactants. So this activated complex, we'll talk about that a little more. The activated complex is very temporary. Sometimes when chemists are studying chemical reactions, they can actually get a picture of this activated complex with the right instrumentation, but it's very temporary, maybe in the order of milliseconds of lifetime for this activated complex. So what is this? So when we're talking about the energetics in a chemical reaction, we can write this, draw this diagram, this plot of a, it's called an energy diagram or energy profile. So on the left side, this is kind of blotted out. Sorry about that. This is potential energy. So this is the potential, the y-axis is the potential energy of the compounds. And if you remember back when you studied enthalpy in Chem 1A, or Chem 2A, I should say, that the potential energy of the reactants related to the products determines whether the reaction is exothermic or endothermic. In this case, the potential energy of the reactants is greater, higher than the potential energy of the products, so we have an exothermic reaction. That means energy is given off when the products change into, excuse me, the reactants change into the products. But this reaction profile has a big hump in it. And this hump is called the activation energy. This is the energy required of the reactant molecules in order to break the bonds in the reactant molecules and form the new bonds in the product molecules. So that's how much energy has to be, that's how much energy these molecules have to have when they collide. Of course, what we said previously, the energy isn't the only thing that's required, the correct orientation is also required. And so even if the molecules have the right activation energy, if the orientation isn't correct, no reaction will occur. So both things have to be present when the molecules collide. They have to have the correct orientation, and they have to have enough energy to overcome this activation energy barrier. Sometimes we call this an energy barrier. The transition state that I showed on the previous slide is right at the peak of this activation energy. This is where that transition state structure occurs. Okay, next slide. Let's see what we've got here. Come on, slide. Let's go. There we go. Okay, so there's an equation called the Arrhenius equation, which relates the reaction rate constant to the activation energy. And that's shown on the left side here. So this is the typical Arrhenius equation, where K is the the rate constant. A, in this case, it has lots of names. They call it the pre-exponential factor or the frequency factor. And the frequency factor has both the orientation and the collision components in it. So the orientation goes in, or the orientation and the concentration components in this frequency factor or the pre-exponential factor. Then the exponential, so this function, the function of K to T, it's an exponential function. And we have the activation energy over the gas constant over the temperature in Kelvin. Now, if we take the log of both sides and after log of both sides, we've seen this before, you end up with a linear equation where the rate constant is proportional to 1 over the temperature, and that forms a straight line with the slope of the activation energy over the gas constant. So this is the way, if you do a chemical reaction at 2 temperatures, and you can find the rate constant at both of those temperatures, you can calculate the activation energy from this equation. Or if you do even better, if you can find the rate constant at multiple temperatures, you'd even get, you can do a linear regression on that plot and get the activation energy. The intercept is the value for this frequency factor. So what does this look like? Here's the number. Here's another graph showing the number of molecules on the left side and the energy, the kinetic energy that they have. It's kind of a graphical representation of how many molecules have enough energy to overcome that activation energy barrier. So in this case, if the activation energy is on the right side and it's labeled the higher activation energy, the shaded, darker shaded area shows that only a few molecules have enough energy to overcome that activation energy barrier and result in products. If we have a lower activation energy, we have more molecules that have enough energy to get over that activation energy barrier. If you increase the temperature, what you've done is you flatten this curve, this energy, this curve that shows how many molecules have the required energy to get over the activation energy. And what you see is there are more molecules as you increase the temperature, the kinetic energy of the molecules goes up. And so there are more molecules that have enough energy to go over the activation energy barrier. So in this case, T1, which is the red line, is less than T2. So T2 shows you a higher temperature that there's just more molecules. That's what the y-axis is, how many molecules there are. So we have a worksheet here to look at these. So I'm going to switch to the worksheet now. So I hope you can see this. Let's see. Some reason. So let's see. Preview. Right, so I think I got that. So hopefully you're seeing this on a big screen. So this is worksheet 5. So there are two problems here. The first problem, I've done most of it already. So it says using Excel and the Arrhenius equation, plot the following data to determine the activation energy of this reaction. So we have a reaction here, and it looks like it's balanced already. And underneath it, I have the Arrhenius equation written. And then transform it into its linear form. And if we want to plot a linear, if we plot the inverse temperature versus the log of the rate constants at these different temperatures, we should get a straight line. So over on the left side are the temperatures that the reaction was done at, 298 up to 338 Kelvin, and the corresponding rate constants that were found. So if we plot these, we take the inverse of the temperature and take the log of K and plot the log of K along the y-axis and the inverse temperature along the x-axis, the slope will be equal to the, right here shown here, the slope is equal to minus activation energy over R. We can rearrange that to find the activation energy, which is this R times the slope equals the negative activation energy. So it's a simple algebraic rearrangement here. Multiply both sides by R. I don't like, we're trying to find the activation energy. So I don't like the negative E. So I'm going to multiply both sides by -1. Negative, multiply both sides by negative. So we end up with minus R times the slope equals the activation energy, okay? So I did this plot already. I was going to do it live, but it wasn't that easy for me to get this plot on Excel. I guess I'm a little rusty. It wasn't very hard to change the reaction, the rate constants into the logs. That was pretty easy, and it wasn't very hard to get the inverse temperature values, but it was hard to get this plot. So anyway, I finally did get it, so I just put it in here. So this is what the plot looks like of the rate constant versus the inverse temperature. So it's a nice straight line, just like it should be. The R squared, which is called the correlation coefficient, is 0.9997, which is very good. This is something I think you're going to do in lab. You're going to determine the activation energy per reaction in lab, and I think you're going to do that next week. So you might do it this way, or you might just do the 2-point system, which is how we're going to, that's the next example, is how to calculate the activation energy using just 2 rate constants and 2 temperatures. You could plot 2 points also. You know, if you just had these 2 points, you could do the linear plot on those also and get the slope. When you do it in Excel and you do a lin, it's called a lin-est function that does the linear regression on these points, you get the slope right here. So the slope is minus 12392, 12,392. So I'm going to write that up here. So we're going to find out our activation energy here. So we have minus R. And the R we're going to use is the gas constant, and it's, if you look at the table up here, this is the one we use because the temperature is in Kelvin. And our answer then will be joules per mole. That's what our activation energy will come out to, joules per mole, which is what we use in chemistry. So we're going to use the R value is 8.314. We're going to multiply it times the value of the slope, which is negative 12,392. And that's going to equal our activation energy in joules per mole. And so I'm going to calculate that. Let's see, negative 8.314 4 times negative 12,392, and that equals, we can do 4 sig figs, 103,000. So it's 1030, we'll just round it off, 000, and it's 4 sig figs, so it's really that zero is significant. The 100 zero is significant. And it's joules per mole. That's our activation energy from the plot. Now, sometimes, because that's kind of a big number, we'll report that as kilojoules per mole. So we write this as 103.0 kilojoules per mole for activation energy for this reaction. So the hardest part of that, once you have the slope, it's easy to calculate the activation energy. For me, the hardest part was getting that plot. Okay, so if you're familiar how to get the how to do these graphs, this is called a scatter graph in Excel. Then this is a pretty quick way of finding activation energy. Of course, the lab work is so hard. Finding the rate constant at different temperatures is a difficult part. All right, here's our second problem. So now there's a way you can take that Arrhenius equation, and if you divide a one rate constant by another rate constant, you end up with this equation. If you want to practice your algebra, you can do that, but this is what it turns out to look like. So it's the natural log of K2 over K1 is equal to activation energy over the gas constant times inverse temperature 1 minus inverse temperature 2. So using this, we can also calculate the rate constant. So what does that look like? Well, we still have to do some algebra to find the rate constant. So we can take the log of K2, I'm going to rearrange this over K1 and divide the whole thing by 1 over T1 minus 1 over T2. And that's going to equal EA over R. So if we multiply the whole thing times both sides by R, we'll get R times, I'll just put all this in brackets, log K2 over K1 divided by 1 over T1 minus 1 over T2. That's going to equal our activation energy. So let's see how that turns out. So at the top we have, you can use any two values of temperature and rate constants. It doesn't matter. It probably won't come out exactly as our linear regression because that's more of the average of all of those. But it should be close because our correlation coefficient in that plot was very good. So let's just pick two temperatures, and I'll pick the top two. And I guess when you work on this yourself, you should pick two other temperatures and see if you get the same thing. So we're going to use this value for R, and I'll do the reaction. So we'll call this 1 and 2 here. Okay, so I'm just going to plug in the values in my calculator, and we're going to see what we get. So I think I might be able to do this straight away. I'm going to try it. So first of all, I'm going to take K1, which is 1.74 times 10 to the minus 5, or 10 to the negative 5, and I'm going to divide it by K2, which is Okay, I already made a mistake. We're supposed to take K2, which is 6.61 times 10 to the negative 5 and divide it by K1, which is 1.74 to the negative 5. So we've got that value. That looks about right, K2 over K1. And we'll take the log of that. That term, I'm going to write this down. So log, I'm going to write these values. Log of K2 over K1 equals the natural log. So K2 over K1 is 3.80. So that value is 3.80. 1.335. Let's put an extra 1.335. Okay. I'm going to take that value and divide it by 1.335. Divide it by, let's see if I can do this. Temperature 1, which is 298. 298, and I'll inverse that. Minus temperature 2, which is 308. I'll inverse that. With my parentheses. If I do that, I get 12,253. So when I divide this 1.335 by 1 over T1, so 298 minus 1 over T2, which is 308. You see that? Let me guess you can see that. I get 12,253. So I'm going to multiply that by my R, which is 8.314 times 8.314. And I get 101.900. I'm going to round it out. And that's joules per mole. And if I want to change that to kilocalories, it's 101.9, kilojoules per mole, not kilocalories, kilojoules per mole. And that's my activation energy. And you can see that 2-point value came out pretty close to the value we got from the linear regression. So if you do any 2 points, they should come out something like that, 102. I did 2 other points earlier, and I got 106 kilojoules per mole. So that's how you do the 2-point method. You have to be careful using your calculator on this to make sure it's doing what you want it to do. That's the only difficulty that I've ever had doing these, is just making the calculator do what I want it to do. So to the next question is, what method is the more accurate? So I think the method that's the more accurate is the one that uses the most points. And that would be the linear regression. What method is easier? I'm not sure. Depends on how fast you can do linear plots and how fast you can do this. So I'll let you answer that one. It's probably different for every student or chemist doing this. So that's the end of this lecture. Let me stop the share. Guess I already stopped the share. Let's see what happens. I hope this worked. Come back. And oops. So that's it for chapter 12. So if you have any questions, I'll have office hours on Thursday from 10 to 11. I sent out an announcement with the password for that. So if you need help, just check in then, or if you need help before that, send me a text or email. Goodbye.